you guys able to hear me? Guys, please confirm if you can hear me.
Yes, we can hear you.
Okay, thank you very much. All right, so we're just gonna go with the last class for this course. Okay, we're just gonna continue with quantum computing and machine learning. All right, so yesterday we've learned that the difference between the classical physics and quantum physics can be measured in terms of energy, of the state. We have the properties. So we've seen many differences between classical and quantum view, right? So, for example, when we talk about particles, we say that classical particles are just particles. So we look at small particles as part of the big particles, but in quantum, we're looking at different levels. So we're looking at particles and the wave as well, where we have what we call a wave function. And we also have the concept of superposition. So when we talk about computers, in the classical way, you have information being exchanged in binary. So we have a bit, which is 0 and 1. So a bit can only be a 0 or a 1. But in quantum computing, we don't have bits, we have qubits, which means that the signal can be at the same time 0 and 1 at the same time. So, so we've compared them in terms of energy, state of motion, properties. Okay, a clear example was the pendulum, how it works. That was a clear example of how we have the difference between quantum and classical. So some basic concept of quantum mechanics. We need to note that in quantum mechanics, we talk about quantum superposition, quantum entanglement, and quantum uncertainty. So when we talk about quantum superposition, remember I just mentioned how we're dealing with qubits. Yeah. Okay, it's a full screen. So we have quantum superposition. That means that when we're dealing with qubits in quantum mechanics, we can have a 0 and a 1 at the same time. Okay, so basically we have similar to waves in classical physics. The result of superposition is just we'll state that it's a state that will be a quantum state. So what does it mean? It means that we're going to have the whole wave properties and the quantum state as well, and the quantum systems. So we're going to have the wave properties and the quantum system. So you need to note these are the few things that you need to note. So basically, in your questions, there can be like true or false. Some of the basic concept of quantum mechanics is that quantum superposition embodies the wave properties of quantum system. So that can be a true. So basically, most of these statements, whenever you see things like concept, so you must understand these will be part of true or false questions. Okay, so you need to know that mathematically, quantum superposition comes from the linearity of Schrodinger wave equation. That means that the linear combination of equation solution is also a solution of the equation. So we have quantum superposition here. So when you think about classic physics, a particle has a specific state. For example, if I look at a ball, the ball is either here or there. So there is a specific state with that. But in quantum physics, when we're talking about particles like electrons, photons, or atoms, these can exist in a superposition of multiple states at once, okay? Until you can measure them. So there's many states of that. So when you look at an electron, for example, it can have many states, okay? So when we look at that, we understand that when we talk about state, the classical physics, an object can only have one state, you know, it's either up or down. But in quantum, we can consider it being up and down at the same time. Okay, so those are certain things. So when we talk about quantum entanglement, what does it mean? It means that when we can take two particles, we can entangle these two particles. So we put them in an entangled state. It means that if we can create a certain motion, for example, that's spinning, so when maybe the first particle spins upwards, the second particle spins downward. So basically, when we try to observe it, we are not picking up a specific orientation. So when we measure it, we can measure it makes the two particles look as if it was one particle. So it's going to be very difficult to get the difference between the one from another, okay? Regardless of the distance, the spin orientation of the other particles. So that is when we talk about entanglement. So basically, when we talk about quantum entanglement, this is just an effect in which two or more particles can be correlated, right, in such a way that when we look at the quantum state of each particle, we cannot describe independently which one is which one. Okay, so let's say we're spinning it, so we have one that will spin up, one will spin down, but we cannot see the difference between the two particles. Yeah. There's a lot of mathematical calculation that comes into quantum, but we're not really going to go into details about that. Okay, in terms of quantum uncertainty, we need to note that the position of momentum of a particle cannot be determined at the same time. So these are true or false answers. Please note that. Okay, so the smaller the uncertainty of the position, the greater the uncertainty of the momentum. Okay. Okay, in terms of the development history of quantum computing, basically when we talk about quantum mechanics, which has been established since 1935 by Einstein, and it has been growing in different areas. For example, we have from the 1981 up to 1996, close to early 2000s, we have a development of quantum computing theory. And then from 2011, remember what we say, now we have an availability of a lot of CPU, GPU, we have many servers, so we have access to many computing power, so we can actually create many advanced technologies with that. So from 2011, that's where we have commercial quantum computers. So we have quantum computer engineering, so where many computers have been released that can be classified as quantum computers. Okay. So quantum computing can be applied in many scenarios when we're dealing with AI, when we're dealing with biological computing, material simulation, we're dealing in fintech, logistics, transportation, security. So we have many areas where quantum computing can really be used. So we're looking at, for example, in AI. So we know that when we're looking at quantum because we can classify ourselves as we are in the NISQ phase. So this means that in the noisy, to be noisy intermediate scale quantum phase. So this means that the quantum computers today that we have about 10 to 100 of qubits. So remember, in quantum computers, we're not talking about bits. So information is not sent in bits, but it's sent in qubits. Okay, it's sent in qubits. So with the NISQ, in the NISQ era, quantum computers have 10 or 100 of qubits, right? But the problem is they cannot really perform large scale of quantum computations. Okay, so they mostly rely on the quantum processors. Okay, so they rely on quantum processors. Remember, all these platforms that we have can give us access to processors that are using quantum computing technologies, depending on how big our model is or how big our project is, so we can get access to that. Okay, so there's a way that you can create, like some people would like to create like a model by combining at the same time quantum computers and classical computers, just because when we have quantum computers, you have certain issues that can really happen. You need to know that quantum computers are noisy, you know, so there's a lot of issues like that. So basically, some people maybe use an hybrid approach. That means that they can divide the task into class by using classical computers and quantum computers at the same time. So basically, the classical computers can maybe control things like data preprocessing, certain optimization, you understand? So kind of decision making of the whole system. And then you take your quantum computer to just try and solve certain problems where quantum advantages is possible, you know? So when you look at things like linear algebra and all those calculations, matrix calculations, you think, okay, maybe it's better to use quantum computers for that, okay? Because you need to understand the quantum circuits really run on the GPU. Okay, so on the Q, they call it a QPU, which means that a quantum processing unit. So you need to know that. Okay, so there is many algorithms that are set to work in such a way, like to use quantum computers. You know, there's many algorithms they can build model by using those algorithms. Okay, so you have it in other areas such as in logistic, transport. Yeah. Okay, basic concept of quantum computing. Remember, this was one thing we've said: quantum bit and quantum state. So bits are mostly used in classical computers, right? So in classical computers, we use bits. That means that a bit will be a 0 or a 1. So the signals on the computer understands the signal can be a 1 or a 0. So we cannot have both at the same time. It's either a 1 or a 0, on and off. So think of it that way, on and off. But when we have quantum computers, we have data in qubits, right? So these are the units of data in quantum computers. So the qubit can have a state of a 0 and a 1 at the same time. Or it can have a linear superposition. So you have this in this pen, okay? So these are just some formulas. No need to really memorize them. So we have, if you hear about gates in electronics, when we're looking at some gates, we have things like OR gate, NOR gate, AND gate. Okay, We have XOR gate. So you have all these type of gate that you can have in classical logic, the logic gate, right? So is there anyone that has never heard about logic gate? Anyone who has never heard about logic gate? Yeah, anyone? Okay, so basically the logical gates will actually be kind of, think of it like building blocks of a circuit in computers. So this will have an input. So here we have our input here, and this is our output. So in this case, for example, this is an OR gate, right? So we have an OR, NOR, and all those things. So if we look at, for example, an OR gate will mean that these inputs, you have two inputs here. So one of them, so if one is 1, the other one is 0. Remember, this is a classical case now. That means we have 1 or 0. So if the input, we have two input like this, we have a 1 and a 0. So here it means that the output will be 1 if at least one of them is 1. That is an OR gate. So we either have, if we have, for example, a 1 and 0, we have an output of 1. If we have what you call this, a 1 and 1, it's going to give us a 0 here. So it needs to be one of them only. So it's input 1, let's say we call it input A and input B. So it either inputs A or B. One of them must have an input 1, then the output of the circuit will be 1. Okay, so when we talk about a NOR gate, a NOR gate, it's the opposite of OR. So it's the opposite of OR. So it's a not OR, right? So what does it mean? It means that the output will be 1 only if all inputs are 0. Okay, so this is a NOR. So a NOR means that we don't have a 1. So if we have 0, 0, the output will be a 1. Okay. So in the exam, the question can be, what's the output of a NOR gate if both inputs are 0s? So we know we're going to have a 1. So we have a 1 only there. So this is the OR gate. So the NOR is the opposite of OR. So now when we say AND gate, so an AND gate, obviously, it means that both inputs will need to have a 1. So if both inputs, so A and B, are 1, then the output will be 1. Any other case, we have a 0. Okay, and then the NAND, obviously the NAND will be the opposite of AND. So it means that it's a NOT AND. So a NOT AND, which means that the output is 0 if we have a 1 and a 1. Okay. And then we have the XOR. So the XOR will be an exclusive OR. Exclusive OR, that means that you see, when we have the OR gate here, when we have the OR gate, it means that if we have 1, 1 in the OR gate, we're still going to have 1. So it needs to be 1 or the other one. But in the XOR gate, this is an exclusive OR, which means that it can only be 1 0. That will give us a 1. If we have 1, 1 in a XOR gate, it's not exclusive. So exclusive means only 1. Okay. So, and then the X no will actually be an exclusive no. Remember what was the no? The no was we need to have 0, 0 to have 1. So an exclusive no will be when we have 1 and 1, it needs to give us 0. Okay. So that is what we have there in terms of in terms of in terms of logical gates. Okay. In terms of logical gates. Any question on that? Any question? Any question? Yeah, but when we have the quantum computers, it becomes something else. We have superposition there. So one input can be a 0 and a 1 at the same time. So it's not like here where we have 0 or 1. Okay, so that's the problem there. Okay, so that's what we're going to have. Okay, so when we have these, now when we have these buffers, so the buffers can be something like the same output as input. So if we have a 1, it show has a 0, a 1 as well. So if you have a 0, it shows as a 1. But in the note, it's just the opposite. So if the signal is a 1, it's give us the opposite, which is a 0. If it's a 0, it gives us the opposite, which is a 1. Okay, but in quantum logic, we have multi-dimension signals here. Okay, so you need to note that quantum gates will often use matrix representation. True or false, quantum gates use metric representation. True, these are metrics. Okay. Okay, so these are just example of gates that you can see. Okay, so this is a representation of how the classical circuits may look like. So this gate here, for example, here we have this sign here is a sign of a or, right? This is a or. When you have a no, we're gonna have that small circle there. When you have an N, it looks like a D. An N will be like a D with that. An XO, you will have this. An X no, you will have that. And then we have a buffer and that. So in this case now, what do we have? What type of gate is this, guys? What type of gate is this? Can anybody tell me what type of gate is this? What type of gate is that?
It's an AND gate, sir.
Yes, that is an AND gate. So we're going to have an AND gate here. It means that if we have signals, now the signals are going to come from A, B, and C. So think of these like plugs. So if we have maybe a 0 here, okay, so let's see. Let's say we have a 1 here. We have a 0 here. And then we have a 1 here. Okay, so we have 1, 0, 1. Okay, let's see. What will be the output here? What will be the output here, guys? What will be the output? Guys, what are we going to have as output here? If in this input here, we plug a 1, a 0, and a 1 here. So when we get to this point here, what will be the output? What signals are we going to have? What signal are we going to have, guys? Guys, that should be easy. What signal are we going to have? Sorry?
Zero.
Yeah, we're going to have a 0 because this is the AND gate. It means we're only going to have a 1 if both of them are 1. So here we're going to have a 0. So here we have 0 as a signal here. And then we go here. What signal do we have? What do we have here? What do we have here? So we have
I think
0.
it's a 1.
Yeah, here we're gonna have a 1 because this is a OR gate. So we have a 0 and a 1. So this is connected here. So we have 0 or 1. So we have a 1 here. And then here, what are we gonna have? What are we gonna have here, guys?
Zero.
Yes, 0 here. And here,
Zero.
0, yes. And then what are we gonna have as the final output?
Zero.
Yes, we're gonna have a 0. So which means that if you picture this as a signal which combine these buttons here, so these buttons send a signal of 1, 0. So now if you have this type of circuit, it means whatever signal is not going to be sent. So you're going to have a 0. So there will be no output there. So if this was supposed to turn on the light, so this will not turn it on because it's 0, because of the way you did this gate here. Understand? So once we have different signals here, obviously we're going to get a different outcome here. So this is basically how you have it in the classical circuits of a computer, normal computers that we have. That's how signal comes. Okay, but if you using a quantum circuit, in a quantum circuit, it's different. So in a quantum circuit, one output can have two states. That's the thing. So we can have 2 states, and then we have a quantum addition circuit. Okay, so that's one of the difference with that. Okay, so we need to note that the maximum entangled states of the 2 qubits is called the Bell state. So when we talk about a Bell state, you must understand we're talking about putting together 2 qubits which are in a state of entanglement. That means they're in a state where you cannot differentiate between one and the other one. Okay, so that is the Bell state. Okay, so okay, so okay, that's fine. And then here is just a few formulas in terms of general purpose quantum algorithms. So we have different algorithms here which are calculated differently. So if you want, for example, to do a factorization, this is math, you want to do factorization. In a classical, we have single day, but in quantum, we're going to have different formulas. Okay. So in terms of quantum algorithm, when we're training a model, So we have our input that will bring there. So in a classical computer, so this will go, all the signals will just go in a neural network as they are, right? But in quantum computers, they first goes into a quantum circuit, then they can go into the neural network and go to the output. So it's gonna have different, okay, so different application scenarios of variation of quantum algorithm. So these are just some application scenarios like in machine learning and different mathematical applications, and different type of calculations. Okay. When we talk about quantum chemistry, what we mean by that is when we use quantum chemistry, when we apply quantum mechanics in chemical systems. So that's why I was talking about all the electrons, atoms that can be at the same state at the same time. So we basically use those theories. Okay. So this is just a quantum approximation algorithm. So it's okay. So this was an example. So this is the Go play. This was actually how the Go game was being played. So when you play the Go game, AlphaGo, that was trained with deep reinforcement learning. Okay. Remember in 2016, the first AlphaGo beat Lee Sedol. So Lee Sedol, which was the champion of the world, was beaten in 2016. And then in 2017, they trained another AlphaGo that was also able to defeat the running champion at the time. Okay, so when we're looking at that, now we look at this classical machine learning, which have created this. So we didn't really need quantum computing to create this type of scenario, because it was just a supervised learning or unsupervised learning in terms of using reinforcement learning. So we use reward and punishment to let the game play against itself like 1,000 times and learn about different patterns. So when we're looking at these technologies here, we've been able to work in such fields such as solving classification problems, image recognition, and learning behavior of different scenarios. So when we look at that now, we could do it without quantum computing. Okay. So, but with quantum computers, it can be more advanced because we can introduce other concepts. All right. So that is okay. These are just some advantages of quantum learning. Okay. These are just some theories that you can go through. Okay, so, and then remember we have MINDS4, which is the framework. You have, in MINDS4, you have a part of MINDS4 which is specialized for quantum computing for quantum computing. So this is called MINDS4 Quantum Computing Framework. So that framework is when you want to create your AI models by using quantum computing. So you can have access to that on these platforms, right? So basically, when it comes to quantum computers, remember when the model will need to use the what you call that, the computing power in order for the model to learn from the data and do everything. So you will basically have to use quantum computers, and quantum computers, all the CPU, GPUs, Essence, and QPU. So you're basically going to use your CPU, central processing unit, your graphical processing unit, all your Essence servers, and your quantum processing unit. So when we look at that now, we can be able to predict whatever the AI is doing. Okay, but if you don't use it, you will use just a simple neural network with some CPU, GPU, and assets. So without quantum computing, you can use the normal mind for deep learning. Okay, but there is also a quantum computing framework which can make your algorithm better. Okay, so the evolution of minds for quantum. So from 2021, we've had so many improvements, right? Up to maybe 2022, where there has been a lot of CPUs, quantum circuit simulators. So they keep upgrading different, and then you can create different things. That's why you can see nowadays there's so many AI tools out there, because now it's very easy to create such a powerful AI tool because of these computing powers that we have. All right. So we have a very good experience in terms of using quantum computers straight from the cloud. You can do that to create all your neural networks. In terms of the performance, we are already on 32 qubit, right? So this is a very good performance in terms of your quantum computers. All right. Okay, so these are just some performance of the minds for quantum. Yeah, so this is how you can see the process, how simple the process is. So you can install it, right? You install your minds for quantum, right? So you can install it on your system. Which means that you can install, if you go, for example, you use Python, right? You can use the pip. When you talk about pip install, this is in Python. So when we say, for example, pip install mind quantum, so it's going to install minds for quantum on your system. So you can do it on a Mac OS, on a Windows, or on a Linux. Okay, so, and then you need to understand there is many places where you can get tutorials on quantum circuits, quantum measurements, and all this information about quantum computers. And then you also have many APIs that will help you really navigate with this framework and get access to certain algorithm that will you will use in your scenario as well. Okay. All right. So these are just some steps that you can look at in your notes. This is how you can be able to actually create a project, create a file. These are just some user guides that you can go through. So you can see this. We are on a Python. We're writing in Python, and we can just import the dependency. That means we can import NumPy, obviously. So, and then we can actually import Mind Quantum, because we've already installed Mind Quantum. So from Mind Quantum, we can actually call whatever we want to call, as we're going to use it in our calculations. Yeah. All right, guys. That will be all for this. So what I'm going to do, by tomorrow, I'm going to post a summary of everything like we did with big data, and also some of the previous exams questions. After you've gone and prepared properly, you will have until month end to submit your mock exam. Remember, we spoke about that, but I will confirm the exact date, but it's close to month end, so basically after next week. So you have all this time to prepare and write your mock exam. Yeah, so we will do that, and if there is any video or any information that I will need to record and post on YouTube. I will do that and let you know on the WhatsApp group. Any question? And guys,
Munir,
yes.
will you be able to share these notes? Because those questions, I'm gonna want to try some of them, especially the